All right, multiple linear regression, here we come. So I have a project open here in R called McDonald's, and before we get into running regressions with many x variables, I want to give you a look at a tool that might be helpful in your research. So suppose you have two separate data sets, because all of your data might not come from the same source, but you need to connect them somehow because you need to have one data set at the end with all of your variables in it so that you can create graphs, run regressions, all of that, right? How do you connect them? Okay, well, there's a simple way to do this. So if you see in my folder here, I have got a file called regions.csv and a data.csv. So my situation is that all of my McDonald's prices are in data.csv, and it also says what state the restaurant is in. So we can look at this here. If I go, let's call this my main data. Doesn't matter what you would want to call it. All will work. Read.csv. Press tab. I want this one. All right. Main. So each of these is a McDonald's restaurant. I've got the price for a Big Mac meal, local minimum wage, some local characteristics. But suppose I want to know what region the state is in. I don't have that here. I want to know if it's in the Midwest or South, etc., right? But what I can do is bring in, I'm going to put this at a higher, line number 7, read CSV, and bring in this regions data. Here's what it looks like. So now it says, well, Alabama's in the South, Alaska's in the Pacific, etc., right? And sure, I could go into R and, I could go into Excel and add a column and manually hand enter all of these, but hand entering data stinks. Plus, in your data, there might be hundreds of thousands of rows. It's just not going to work. We need a way to automate this process. I need a way to automate it to say, if this is Hawaii, then it's Pacific. If it's South Carolina, it's South. So I want to get a new variable over here on the right side of my main data that says what region this state is in. Okay. I want this column right here, region, to be tacked on the right side of main, but it needs to match, right? So it needs to find all the Alaska restaurants and make sure it says Pacific in the region variable there. Okay. So what I'm going to do is pipe from my original read CSV with the original data file and say, keep doing some stuff with it before we save it to data. And what I want to do is match the state names with the region. So this is called left join. So here's what it does. It takes a pair of data frames and combines them. So the first thing you need to tell it is which data frame should I be combining with data, and the one we're adding in is called regions, right? So we want to tack on this regions data frame. And the next thing we need to tell R is how to combine it. Like, how do I know where things match? Okay, and so this is where we're going to say by. And then in parentheses, you put the variable name. Now the variable names need to match, so this needs to be state name, and this needs to also be called state name, and the values need to be identical. So this cannot say CA for California, and over here it says California, they won't match, and it won't be able to say that, oh, CA is in the West. They need to have the same values, same variable name. But once that's good, we just say, okay, match on state name, and then what R will do is it'll find any mentions of Alabama in the main, and it'll take all of the variables. I've only got one, it's called region, but if there were more over here, 2, 3, 4, 5, it'll take all of the variables that characterize Alabama and tack them on onto the right side of main for all of the instances of Alabama in state name. And then it will repeat that for every single state in here, so that your main data will now, on the right side, have all of the variables from the regions data as well, matched by state name. And so let's run it. And then we might do a little sanity check. So open main, and then let's just make sure. State name Hawaii, it should say Pacific. South Carolina is in the South. Texas, South. Don't tell anybody from Texas that. Okay, but it worked. Okay. The other thing you might run into at some point when you work with your data is you've got way too many variables and you want your sanity check, you're scrolling back and forth like this. This is easy to fix. Pipe, and then order. Order says, order my variables in this way. And you don't have to type in all of them. If I just say put price, order price. That just tells R, make sure price is all the way on the left. Hold on. Price. There's a price there. Let's check with ChatGPT. In R, using tidyverse, how to reorder my variables. Everything. Okay, let's try that. Or it looks like relocate. Let's try relocate. Relocate price. That did it. Now price is all the way on the left. But the whole point of this was not necessarily to move price there, but to just do a sanity check. So what I really wanted to do was state name, and then what's it called? Region. Relocate those two to the left side so that when I do this little sanity check, I can go, yes, it's working. So relocate, that will be your friend. So joining datasets, done. We did it. Left join. The way that you always do this is start with your main data, whichever one has all of the stuff you want in it, and then join in this additional information with left join. The reason you would want to do it in that order is because suppose I have no restaurants in Washington, D.C. in my data, then R will just leave off all of this because it knows this is the one I really want, and I just want to tack in any of this additional information if we need it. And if it doesn't find any restaurants in D.C., then it just won't do anything with this. But if I do this the other way around, if I did region and then left join main based on state name, it would leave DC in. It thinks this is my data of interest, and then it would just make empties over here for the restaurants related to it. But I don't really want this in my data if there's no instances of DC restaurants. Okay, joining datasets, we did it. Next, we know how to run simple linear regressions. We're good with that. But what if we wanted to make the case that two variables are correlated with each other? Okay. Well, there are a lot of ways to do this. So the first thing I'm going to do is show you that we can use this function called correlate. And it comes from this package called corrr. I think this comes from correlate R. You would need to install it if you haven't before. I'll do it anyways and see if it wants to update. Nope, don't need to restart. Update it and then make sure you load it with library. Okay. Now here's what it's going to do. It's pretty simple actually. All you need to tell R is correlate and then put in there a data frame. So main. And it's going to show me the correlation matrix of all of the variables in the main data frame. So when we run it, what it gives us here are called correlation coefficients. Here's how correlation coefficients work. They have a maximum of 1, and if you get a 1, this says these things are perfectly correlated in the sense that as x goes up, y also goes up, if x and y are the two variables we're looking at. Also goes up by a proportional amount, always. -1 is the opposite. That means it's a negative correlation. This is the minimum it could ever be, -1. And it says as x goes up, y goes down by perfect proportions all the time. And therefore, anything that's negative suggests a negative correlation between these two variables. Anything that's positive suggests a positive correlation between these two variables. And so just one little coefficient in here will allow us to determine any correlations. So for example, let's take, here are all the correlations with the price variable right here. So what this is showing us is that there is a positive correlation between the population density in a city and the price that the McDonald's is charging. This one shows that there's a negative correlation between unemployment rate in the city and the price that McDonald's is charging as well. Okay. So this is one way to do it. Word of caution, this variable called county FIPS in my data is really a categorical variable. It's like a coding system for counties. It's a number. Also, R just thinks, oh, it's a number. Well, let's run correlations. So it's going to correlate the county code with all of this other stuff, even though we shouldn't really be doing that. It's really a categorical variable. We could fix this though. We could say mutate county underscore FIPS equals as dot factor, which tells R treat this like a factor variable, which for R is a synonym for categorical. And then when I run correlate, it just won't even include it, because why would you run? You can't really find correlation coefficients with any factor variables. Okay. So this is one way. It's not very scientific, or it's not very precise. Like, you won't be able to tell a very fun story here when you say that median income and price have a positive correlation, and the correlation coefficient is 0.48. So if we wanted to tell a more vivid story about how two variables were related, like suppose I want to know does a city's unemployment rate and its price, this one right here, I can already see it's negative, but we can help a viewer or reader visualize this by actually creating a graph. So we could say, you know, x equals unemployment rate. We might, you know, we might decide x's and y's based on what we think is the kind of more causal story. Whichever one seems to affect the other one in kind of a causal sense should go on the x. So here's a scatter plot, and the scatter plot doesn't really show necessarily a correlation. I mean, sometimes you can see it, but what we really want is, of course, smooth, and let's run a straight line. Linear model. Boom. So we have a downward sloping line. It's going to put an estimated standard error in there for us, and the fact that it's a negative line is always going to happen when we get a negative correlation coefficient here. But it's a little bit more descriptive. So it's negative, but it's not super strong, and the scatter plot kind of would help a viewer get a sense for, you know, just how powerful this relationship is. What we can see here is it's not that much. So you can show correlations by just calculating correlation coefficients. You can show it with scatter plots and regression lines added in. Now this is not so great if one of these variables is a dummy. So any tax is a dummy variable. It takes a 1 if this state where this McDonald's restaurant has any state income tax. So the way that income taxes work is there's a federal income tax, and then state income taxes get added on top. Some states don't have any, so we might want to know, how does having a state income tax correlate with McDonald's prices? And, well, let's just look. If we put any tax here, it's going to create a graph, because R is going to say, well, these are just numbers. So sure enough, we can graph this. This looks like a mess. We would never really want to make scatter plots where one of the variables is a dummy variable. It looks awful, and it's not very descriptive anyways. We can do better. So what you might instead do is say, well, let's find conditional means. So group all of my restaurants based on whether or not there is a state income tax there. Group by any tax, and then let's just summarize. Mean equals to mean of price, mean P, mean price. And press run. So this will show, well, the states that have no state income tax, a Big Mac meal has an average price of $11, and the states that do have a state income tax, the average price of a Big Mac meal is $11.50. Well, then that means that there's a positive correlation, right? So as any tax goes up, the mean price also goes up. And so for a dummy variable, we can find correlations by just finding conditional means and comparing what happens to the mean of one of the variables conditional on the values of the other one. Okay. Or we could just run regressions. So, like we could say, we could do simple linear regressions with the two variables that you want to identify correlations for. We know that the beta 1 hat you get from your simple linear regression is just measuring a correlation. So if I do price at McDonald's, dependent on this dummy variable for is there any state income tax, it will tell me, as we kind of just found with a little bit of rounding, the states that do have a state income tax, the Big Mac meal tends to be about 47 cents more expensive. So again, positive correlation, that's what this would tell us. So we did it, showing correlations between two variables. A lot of ways to do it, some ways more descriptive than others. I like descriptive methods, help your reader understand what's going on. So stuff like this, showing yes, it's a positive correlation and here's how much it is. It's kind of a good way to do it. Okay. Now, suppose we want to put many different variables in the same regression model. This is going to be super easy, which is great for us. I'm going to take my data, I'm going to pipe to the linear model. So, just as a reminder in case we're missing this, there's two ways to run your regressions. You can do linear model, then you can say regress price on the minimum wage. But then you need to tell it to use the data main after the comma. I tend to do it this way. It's totally up to your preference. I usually start with the data frame that I want, pipe to linear model, and say, okay, regress price on minimum wage. But then this function is like mad. It thinks you're supposed to put a comma and then tell me what data to use. So okay, fine, comma, and then just put a period which says I'm already piping in the data. So just use the one we're already working with within the pipe. So again, what this regression then tells us is that as minimum wage goes up by $1, that's associated with a 23-cent increase in the price at McDonald's for a Big Mac meal. Now if we want to add in more x variables, because we're worried about omitted variable bias, easy enough, plus is your friend. I want to put in median income as a variable, run that. It'll just add in another x variable. Now, let's go back. I've got this e, whenever I've got this e, I don't want that. Turn scientific notation off. Try it again. All right, so now that I've got two x variables, this says as a city's median income goes up by $1, this minuscule amount is what happens to a Big Mac meal, which, no kidding, $1 of median income in a city is nothing. Some of us would barely pick up $1 if we saw it on the sidewalk. So this is why I like to use this pipe method, because I probably want to rescale this variable and say, don't use median income as the variable there. Use median income in, I don't know, tens of thousands of dollars. So what happens when a city's median income is $10,000 higher than a different city, right? Let me run that. Now the problem here is I didn't save it back. Median income equals to median income. So mutate says create a new column called median income. How do we get it? We'll take the previous median income divided by 10,000. There we go. That says as a city becomes $10,000 richer in median income, the price of McDonald's goes up by about 23 cents if you round. Now note, this scaling of this, we call this a control variable, right? Median income is a control variable. The scaling just helps us interpret its estimate if we wanted to do that. It won't change the estimate for the minimum wage variable at all. It's the same number. Same with the intercept term. Nothing changes there either. So this is really just there to help us interpret what this value means if we wanted to do that. This makes a lot more sense. Okay. Now we could, of course, go back up. I like to put all my libraries together. JTools will make our regression look a little nicer. So let's call this OLS1, and then summary OLS1. Not summary, sum. There we go. Now it only gives us 2 decimal places. We get our standard errors, our p-values, etc. So, with the null hypothesis that the minimum wage doesn't have any correlation with the McDonald's price holding constant median income, we would reject that null hypothesis. The p-value is below 0.01, so it's very unlikely to be due to random chance. Okay. Now, easy enough, because we're just using continuous variables. I could keep adding, right? Unemployment rate. Let's update all of this. Remember, if you add an unemployment rate here and then you just run this again, you're going to get the same thing. You haven't run line 39 through 41 yet. You need to overwrite OLS1 with your new model and then run it. Now we just get an additional variable in there. Totally cool. So we can just keep adding. But all of these are continuous variables, so it's a little bit more straightforward in terms of what's going to happen. We add in the variable and we get back out what we wanted. Okay, but suppose our x variable of interest was categorical. So like, this isn't the best research question, but if my research question was, how does the region that a McDonald's restaurant is located in, how does this affect its pricing? Okay, well, simple enough. We're going to take our main data and run a regression where price is explained by region. We just put the name of the categorical variable in there, okay, and use that data. Boom. And sum OLS2. Okay. Now, to get a sense of our results, what we might do actually before we ever even get there is say, well, let's just see what's going on in this variable. So for categorical variables, you might say count the regions, and we could also, if we wanted to, in these results, it's quite easy for me to see that the most McDonald's restaurants in my data are located in the South. That's the most common region. But if I had like 50 different categories here, it'd be a mess to scroll through here and find the largest n. So I could do a range. A range says take all these rows and like sort them by the highest n. So if I do a range n, there we go. Except a range always puts the smallest values, numerical values, at the top. Easy enough. Put a negative in front of n. Arranged by a negative amount of n. There we go. Now we can see which is the most common region and how common each of them are. Okay. Then when we run this and get to our results here, we're going to see, well, there are 5 different regions in our data, and yet we got 4 dummy variables, which is exactly what we want. We avoided the dummy variable trap. Any categorical variable, if there are 5 categories, we need 4 dummies. One of them needs to be left out. So by default, what R does is it takes, my guess is it's always going to take the category that is just highest in alphabetical order. So Midwest is in the alphabet with the M before all of the rest of these, and it leaves that one out, okay? I didn't get to choose it. Now if I wanted to choose to leave out the South, right? Maybe because I was giving a presentation in Alabama, say, right? And therefore, it makes sense that this is our reference. Our reference framing is the prices in the South. So let's leave that out and then make the rest of the model show us differences in pricing compared to the South. How would I do that? Okay, well, our friend is going to be this function called relevel. Now you can put functions inside of functions inside of functions. You can keep going until you're, blue in the face with functions. So yes, inside of this linear model function, we can use another one that's called relevel, which says take the levels of region and like redesignate which is the reference level. Because for R, the word level is like, when we look at this this output here, R would say, well, there are 5 levels. The minions that work inside my computer would say there are 5 levels to region, right? 5 possible categories. So we're going to re-level it, and all I'm telling it to do is to run a regression of price on a re-leveled version of region where the reference category, ref, equals to south. Okay, so use that as the reference, and all comparisons will occur against it. We run, and this is where R gets mad at me and says, this is only for unordered factors. So I might say, factors, what do you mean? Structure, main, run this, and it will tell us what kind of variable R thinks all of these things are. So CHR means character. Here's factor, because we already redid county FIPS to be a factor variable. It says there's 136 different counties in my data, no doubt. But it also thinks that state and region are characters, kind of like qualitative variables, just a bunch of text. For some reason, R didn't pick up on the fact that, well, within region here, south repeats a bunch of times. It's a categorical, it's a factor, right? So there's a lot of ways you could do this. You could come all the way back to the top and mutate. Region is as factor region. Then we have to go back and run a bunch of stuff. Honestly, if we just do factor region inside of here, and now make sure all of your parentheses are balanced. If you have 3 of these parentheses, you need 3 of these ones. And R will help you do this. You see how when I move my cursor next to a parentheses, it says, well, here's the mate for this one, right? They match. So this one has a mate, this one has a mate, and this one has a mate. We're good. If I do factor region, so again, we're like functions inside of functions inside of functions. That's fine. What I'm telling R is run a regression of price on a re-leveled version of the factor variable version of region, where south is the reference region. Boom. It worked. And now my output is kind of a mess, but we're going to fix that at a later date when we code to make sure that we get something we can read here. But you can still see now we get coefficients for Midwest, Northeast, Pacific, West, compared to pricing in the South. So we did it. We got to choose our omitted category and run regressions that compare pricing there to in these regions. Now, you'd only really be super interested in re-leveling if your main X variable of interest is a categorical variable. So let me make some notes to myself here so I don't forget how to do this. How to re-level a categorical X variable. And I might even make notes about, factor, and then put the variable in parentheses. Tells R to treat it as a factor. It's up to you. All right. Before I got lost, a little side quest. Really only interested in re-leveling if the primary X variable of interest is categorical. Here's why. Suppose you just wanted to use categories as a control. So you wanted to do something like this. Main, LM, price. Because really, it's the minimum wage. That's the point of this research. Region, I'm just going to use as a control variable. So let's call this OLS3. Oh, jeez. Okay. For those of you that like efficient coding, I have a bad habit from a different programming language where I highlight all this. You could have easily just done this. Go to the last line of this chunk with the pipe, press run. R will automatically move the cursor down to the next one, press run again. It'll just keep running chunks as you click run. But anyways, here's where we get, right? Minimum wage goes, as the minimum wage goes up by $1, the price of a Big Mac meal goes up by 22 cents. At least that's the correlation is associated with that. Controlling for region. It still leaves one of them out. It leaves out Midwest because I didn't re-level it. That's fine. This is what I get. Now, we could re-level it if we wanted to. You know, we just really want to have fun putting functions instead of functions, so we can do that. We can say, as a reminder, re-level a factor version of region, and now my parentheses are really mad. I get this red X saying, like, we've got unmatched brackets. Our parentheses need mates. That's correct. Factor region by ref equals to, oh no, south. I think that's right. Now they're all matched. And my X goes away. Perfect. We could do it this way instead. Run, run. We could go through all the trouble, but if it's just a control variable, it doesn't matter what the reference category is in terms of our variable of interest, which is minimum wage. We got 22 cents again. Same result, same standard error, same T statistic. Everything is the same. That is related to the minimum wage variable. So if it's a control, it's fine to just include it as long as R knows it's a factor. Okay, so as long as R knows it's a factor and treats it that way. Because the last word of caution is, suppose I wanted to like control for county. I really don't have enough data to do this in this version of my project. Suppose I did. Suppose I had every single McDonald's restaurant that exists. I could control for what county it's in. And if I told R, for example, I can still do this, at least in the wrong way. I can say, if I was doing this the wrong way, I would say, well, put minimum wage plus county FIPS. And what this would say is, here. Oh, it's not a problem actually, because I already refactored it. So it's treating county FIPS like a factor variable. So because I kind of made sure I wouldn't make a mistake by calling it a factor variable in the very beginning, right? If I hadn't done that and put county FIPS in here, and it would say it was continuous. So then, so like as a double, is that right? No, as numeric. If I hadn't already hedged or gotten rid of this problem, it would have treated it as numeric, and then it would have said, well, every time county goes up by 1, here's what happens to minimum wage. But that makes no sense. What does it mean for the county to go up by 1? Do not make a mistake like this. It's going to throw your entire research for a loop. You're just adding in a variable that doesn't make any sense. So this is why it might make more sense to, from the very beginning, make sure R is treating your variables as the kind of variable that they really are.